Hello everyone. So we're going to move into last unit, unit number 4, and this will be your section 1 in unit 4. So under this section, I am planning to discuss basically about the electricity part, whole thing together. Again, a lot of materials and compressed into this section. In your textbook, chapter 18, 19, and 21 all together, but we are not going to detail for each concept, but we're going to learn them very briefly, learning about the Coulomb's law, electric charge, what is the conductor, insulators, and then we're going to move into electric field, electric force and field lines, electric potentials. And finally, we're going to move into a little bit about the circuits that have capacitors and also resistors, light bulbs, and so on. So those are the main parts that I'm planning to discuss in this section. And let's see your Blackboard page and also the presentation. So as I mentioned, you can always take the break in between because it is going to be little longer chapters in this unit, especially last section, and also section number 1 will be little longer session. Okay, and let's move into the presentation. Okay, so we're going to start with static electricity that you feel in day-to-day life, right? So when you basically try to open your door by using your hand, doorknob, and your hand will create a kind of static electricity in you feel it, right? When you rub something with your hair, then you're going to definitely feel kind of static electricity. And most of the time, I feel that when the dryer, that when I use the cloth drying, you always feel the static kind of electricity, right? So this is everywhere in our day-to-day life. But what is actually happening when you rub the things together, right? So it is depend on the material, but you're going to feel that some different behaviors when you rub different materials. So simple example, if you rub the same material and if you're going to isolate that system, like hanging it, you see that in my negative one is hanging on the wall. So if you isolate the system and if you try to bring them together, then you're going to see they have a kind of like repulsion in between these two, right? And this will be exactly same thing happening, but here if you do it in different materials, you may feel they're going to attract each other. So now we're going to study why they repel, why they attract. That's the part that we're going to discuss first. Okay. And first thing you need to think is atomic structure. We discussed this before also. We have proton, neutron, and electron. Neutron and protons are sitting on the center of the nucleus. Electron is the particle sitting outside. Electron is the lightest particle that can move around. And electron has a negative charge and proton has the positive charge and neutron is neutral. Those things we discussed earlier, right? So now here is the charge that I mentioned about the Coulomb. This charge behavior is the one that we are working in this section because charge has a lot of things to do with the electricity of the materials, right? So now conductors and insulators. Conductor is the material that can conduct the electricity. That means the particles can move around the material. We call it as the conductor. And insulator is the material that there is no charge flow, right? Simple example that you can think is if you have a charge object, if you have a neutral object, if you combine these two objects by using the metal, then some of the particle from here to here will move and then they're going to be both going to be charged. That is called it as the conduction, right? And conductors. And then if I use the wood or the plastic, then nothing will happen. It will stay as the same. So wood is the insulator, metal is the conductor. But there are in-between material like semiconductors. Right? Semiconductors are the material that we use for the computer chips and many, many applications. Those are in-between material that has the property of the conduction and also property of the insulator. Those are semiconductors. Okay. And first thing we're going to learn is the Coulomb law. So Coulomb is the scientist that describe when you have charge and when you have another charge, these two charges should have attraction or repulsion, but that attraction or repulsion amount you will be able to calculate by using the Coulomb formula. What is the Coulomb is saying is that magnitude of this attraction and repulsion is depend on two charges that you have, the charge measured by Coulomb, that size, that Coulomb amount of the two charges, and then also distance between two charges, inversely proportional, and then we will be able to write the Coulomb law by using constant. That constant we call it as the Coulomb constant, that is a constant 10 to the 8.99 10 to the power 9. Okay, so when you increase the charge amount, it will increase. When you increase the next charge amount, it will increase. When you increase the distance between charges, force will be decreased. That's how the force will change according to the Coulomb's law. So now this is another way that you can see it graphically. When you increase the I mean, this is actually Q1 and Q2. That's my typo, okay? Q1 and Q2. So when you increase the charges, it is increasing linearly. When you increase the R, it is decreasing as 1 over R squared, okay? Inversely proportional. So, but it is very important that he did not mention about the direction in the formula. Direction we need to take from our head by thinking if I have positive and positive, they're going to be repulsed. So repulsion we always draw like this, right? Negative and negative also repel, but if I have positive and negative, they're going to attract each other. Important thing is force on this particle and force on this particle are the same according to Newton's third law, right? So force are equal and opposite. If you change one particle, force for the both particle will change because your formula is this. Okay. Okay, so now charge on the electron we discussed earlier. Charge of the electron is 1.602 10 to the negative 16, but it is a negative charge, right? So now if I say the coulombs, that means you are basically saying how many electrons you have it on that particle. That means charge of the any object will be able to write it as charge of the electron times n. How many electrons I have, that will be the definition of the charge of that particle. But that n should be basically a number that can have number of electrons on that material, right? So now if I have 1 coulombs, you will be able to calculate how many electrons are there. That means 1 coulomb divided by this number will give you how many number of electrons you have it in that particle, right? So that will be how you calculate the number of electron on any kind of particle. I'm going to just calculate it by using my calculator. 1 divided by 1.6 equals 625. So I have 6.25 times 10 to the power 19. No, I have 1 in here. 18 electron. This is number of electrons, not units. There is no units, right? Because number of electrons. And so now we know that there is a force in between two particles always. But if there is many particles, how you use the Coulomb. So you need to use individual pair of the particle, and then you need to use the superposition principle by using vector informations that we are not going to actually do for your class, but basic understanding. If you think that two particle, you know how to calculate it. If I have many particle, I need to use the superposition in principle by using vector diagram to find it out. Okay, so now we're going to move into the electric field. Electric field is defined as force per unit charge, right? Force per unit charge, we call it as the electric field, right? So now electric field is a feeling of the charge in when you bring it to the source charge. We'll say I have a positive charge here. This is we're going to say a source charge, source that will produce the electric field. And now if I try to bring another positive charge, what I know, these positive will repel each other, right? Because of that, this positive charge feeling, it is going outward from the source. That is the electric field. That feeling, that test charge will feel, we call it as the electric field. So now electric field will be able to calculate by using force per unit charge that we know, but how is the direction? So direction of the electric field, if it is a positive charge that you're going to bring, then you have the force and electric field, both direction is the same according to this formula. But if your charge is negative, then this is going to be negative. Because of that, you have force and electric field in opposite direction. Okay, so units of the electric field, force per charge, you know that it is newtons per meter. That is the unit of the electric field that we use the symbol E for that. Okay. Okay, so now more informations, electric field, force per unit charge, then definitely since we know the Coulomb's law is this one, earlier we discussed that, and now divide by the source charge, you're going to get this one. So now this is the electric field. Electric field only depend on the field that produced by the source charge. That's why this one of the Q will going to cancel out when you go to here. Right? Because of that, it is independent of the charge you're going to bring from outside. It is depend on the established charge, that is the uppercase Q in here. Okay, I know that I did a mistake in here, not meters, so it is Coulomb. Okay, so it's so sorry for that. I was thinking about divide by distance. Newtons per Coulomb, okay, not the newtons per meter. Okay, so I have the units in here. Okay, so similar to electric force, electric field also, you can use the superposition principle if you have many charges that you need to calculate the electric field. Okay, and now direction, as we discussed, if I have a source charge that will produce the electricity, electric field, that source charge, if it is a positive, that will create the electric field outward direction. Positive charge will create electric field outward direction, and negative charge will create electric field inward direction. So you need to keep that in mind. That will be easy for you to understand what will be the direction of electric field when you have different charges. Those are individual charges that we call it as point charges. Okay, so now if you have system of particles, simple example, positive and negative together, then electric field line is going to start with the positive charge and ending at the negative. This arrow represents the direction of electric field, starting from positive, ending with negative. And always this line are perpendicular to the surface of the charge here and here also. Okay, and it field is stronger closer to the charge. That means you see that here I have lines are very close to each other, denser. That is called it as the stronger field. But here I have a weaker field because electric field lines are far away each other. Okay, so now there is a misunderstanding between electron volt and the electron volt and the basically joules or energy or the you're measuring energy or the volt. So that's the misunderstanding. So now electron volt is actually unit of energy. It's not the unit of volt. It is a unit of energy, because electron volt is 1 electron volt is equal to this much of joules. Okay, it is a unit of energy. Okay, and electric potential is the next step. So electric potential is defined it as it is calculated by using calculus. Actually, we are not going to do it, but electric potential is the basically define it as the energy per unit charge or work done that you have to do to bring the particle from one point to another point. You have to do the work done. That work done per unit charge, we call it as the electric potential. So electric potential will be able to calculate by using this formula. What that means is electric potential is actually a scalar quantity that we can easily work on our problems. So electric force, electric field, we discussed earlier, are vectors, but electric potential is a scalar. But if you have a positive charge, that will give you a positive number. If it is a negative charge, it will give you a negative number, but it is a scalar quantity. Okay. And so this is how, if it is a positive charge, electric potential change with the distance. And this is how, when the charge is negative, electric potential will change. Okay. And so now, since we talk about the potential, we're going to move into equipotential lines and the surface very briefly. So equipotential lines are very important concept that has the meaning of the wordings. That means equal potential lines. So now, if you think about this example, we talked about these red lines earlier. Red lines are electric field lines. Equipotential lines, I have it in green color. That will show you the equal potential points. That means if I calculate the potential on this circle, everywhere I have the same potential. That is, we call it as the equipotential line. And if I calculate in everywhere in this circle, you're going to see a same potential. That is another equipotential line. Right? Those are called as equipotential line. There are very important things happening in here. They are perpendicular to electric field line. Okay, and you can see here I have a simple capacitor, positive terminal and negative terminal. Then I know that electric field lines are those red line, but my equipotential lines, you see that here I have 15 volt. This whole line is 15. So that is called it as the equipotential line. And this whole line is 10 volt line. This is equipotential lines. Okay. So equipotential is important when you think about the work done and things, because equipotential means equal potential. That means there is no work done you need to do to move the particle from here to here. There is no work done needed because no potential difference in there. So now by using equipotential lines also, you will be able to calculate the electric field. Electric field is defined as the change of potential divided by the distance between lines. If you have equipotential plane here, you take the potential difference between these two and divide by the distance between that, then it will give you the electric field approximated value. Okay, but it is going the calculus that we need to do long calculations, but approximate idea is that. Okay, so now voltage potential that I discussed earlier is measured by units of volt. I forgot to tell you that, and volt is the unit, volt. Okay, volt is the unit. In another way, you can see it is the unit of your electric field times the R. That means Newton over Coulombs times the meter. That we can call it as the volt. Okay. Okay, let's move into capacitor. So capacitor is the one device that we're going to start with. Capacitor has different shapes as in real life. We have cylindrical capacitors, we have spherical capacitors, different shapes of capacitors. But in your class, we're going to start with the simplest capacitor, that is the parallel plate capacitor. This one, parallel plate capacitor. In parallel plate capacitor, you basically have two terminals and two plates. So one is positively charged, other side is negatively charged. And so now in this capacitor, we will be able to write the charge of the capacitor as some constant times the potential difference of the two plates. So now this is potential difference, and C is, we call it as capacitance. Capacitance we going to measure by using unit of farad, that will be coulombs over volt. So that is the unit of 1 farad. Okay, so now capacitor, we use the symbol for drawing like two words exactly same, two vertical lines or horizontal lines depending on the circuit, but they are exactly same size. And this is the symbol that we're going to use for the battery. Again, two lines, but they are not same size, positive and negative terminals. Okay, so now capacitor can have the capacitance. Capacitance that I am talking, this is C symbol. C symbol is the ratio of charge to voltage on the capacitor. Other than that, that C value, we are not able to change on our side because it is the manufactured value that is given for that capacitor. Okay, but how that manufactured value change? Manufactured value need to be changed by changing these variables. One is the capacitor cross-sectional area. That plate that you have, the cross-sectional area of the plate is one parameter. Other parameter is the distance between these two plates. If distance is greater, then your capacitance will be smaller, right? When cross-sectional area is greater, then your capacitance going to be increase. When this decrease, that will increase too. And the epsilon naught, I have it in there, we call it as permeability of the material in between these two plates. That is the epsilon naught value that we can use as a constant in here. Okay. But when you have parallel plates capacitor, in capacitor, there is a media in between these two. We usually use the insulator for that. That is, we call it as dielectric. Dielectric, that's the material in between two plates. That also affect to your manufacturing of the capacitor. Because of that, K will be included into the equation. That is, we call it as the dielectric constant. Okay. So that is depend on the material that we're going to use for the manufacturing of the capacitor. Okay, so now many capacitors we have in circuits, we can connect them by using series and parallel. Before that, what the capacitor actually do? In real purpose on your computer, you use the capacitor for what? Capacitor will use to store the energy. That's the purpose of the capacitor, store energy. Store energy for later use. That's the purpose of the capacitor, right? Capacitor will store, then you can use that energy, right? But capacitors can be connected parallel to each other. Parallel means, you see that this one, I have it in here, is parallel line with this three. So those are, we call it as parallel connection, right? Now, if you have parallel connection, combination of these whole setup, we call it as equivalent capacitors. That's what the C equivalent means. So now if they are parallel to the circuit, you can reduce the circuit into here by making these three capacitors together into one. That is called it as equivalent capacitor. That will be adding of all the capacitance you have it on the circuit. That will give you the equivalent capacitor if they are parallel. Okay. Now, a simple example I have three capacitors here. This symbol is microfarad, micro. So if you go to the first chapter, I mentioned about those symbols, microfarad. Microfarad means 10 to the negative 6, basically, right? So now I have the three capacitors. You need to understand they are parallel. They are now parallel in horizontal direction, right? So now they are connected to 12-volt battery. I need to calculate the equivalent capacitor. How do I calculate it? So you have C1, C2, and C3. You just add them. That will be the equivalent capacitance in here. So you have 0.1 plus 0.2 plus 0.3. Everything is microfarad. Because of that, your answer, you can write it from microfarad. It is 0.6 microfarad. So now this calculation is easy, but only thing is you need to really understand they are parallel to each other. When they are parallel to each other, different capacitors, they have different current on the circuit. C is different, but they have same 12 volt. So that is the basically parallel capacitance. Okay. So now they can connect serially too. Serially means you have a single kind of loop. You see that only a single loop in here. They are connected one by one. So that is, we call it as the serial connection. When you have connection serially, since it is a single wire, they all carry the same current, but they have different voltage. Now combination of these all capacitance, we can write it as C equivalent, but in this case, C equivalent will be equal to adding of all the capacitors with the 1 over values. 1 over C equivalent equal 1 over C1 plus 1 over C2 plus 1 over C3. If you have more, you keep adding them. So now the simplified version of that will be here. You can take the 1 over of your final result. Okay, that if they are serially connected. Okay, so now we're going to move into the electric current. So electric current is defined as the charge per unit time. Charge per unit time, we call it as the electric current. Charge you can pump per unit time is the current. So now as soon as you see that, you can see the units. So the charge we measured by coulombs and time measured by second. Now coulombs per second, we call it as amps or amperes. Amperes, amps. Letter symbol A, most of the time we use amperes. Okay. So now when the current carry on the material, so current carry in the all the part of the material, then you can relate that into your conduction or the charge movement, right? So now electric current is basically motion of the charges, right? Motion of the charges, we call it as the electric current. So now electric current is needed to do the work on the your device. If you have a light bulb, you need to light it up. Then you should have current go through your circuit. So simple example is, this is your real life scenario that you're going to see, but this is what your electric circuit that we can draw it, because we are not drawing the bending wires, we just make a line of wire. So now what will happen is, real life, this is your positive terminal, this is your negative terminal, then your current will go through the filament of the light, then it will be light up because of the filament is going to heat it up, and then it will produce the light. Okay. So now to light it up, there should be a current. In addition to that, there should be a power source, right? And in addition to that, there should be a closed loop. These are the three parameters that you should have. You should have current. To have a current, there should be a power supply or potential difference. And there should be a closed loop to have the work on the circuit. These are three parameters that we have it in the circuit. So now you can watch in here, I have three diagrams that basically not connected correctly. Two of them, one is connected correctly. So everybody know that this one seems to me connected correctly to your circuit, because one is in positive terminal, other one is negative terminal. I have a closed loop, everything is fine in there. But if you go to the first diagram, what you see, so this both are positive terminal, there is no connection to the negative terminal, there is no loop. So then this is a wrong circuit. And this one you have the loop, but the problem is you are still connecting to the exactly same terminal. So you should have a potential difference to have a current. Then this is also wrong. Then only the third one will satisfy that three conditions. Okay, so now as I mentioned earlier, current is flowing of particle. But what particle? Flowing of positive charges. So direction of the current is conventionally defined as the direction of the positive charges. That's why if you have a positive terminal here, then current direction will be this way. Okay, so that will be the direction of the current. Positive particle, that means negative particle have the opposite direction of current. Okay, so we are talking about the current direction as the positive particle direction. Okay, so after we learn about the current, next step is learning about the resistor and resistance. So now first thing you're going to observe is the Ohms is the scientist that discovered the relation between relation, or how to get the relation between current and the voltage to the resistor, right? So now if you get the circuit, you have a light bulb, you have the power supply, you keep changing the voltage, and then you're going to produce the current, and you measure the current by using multimeter in the laboratory, right? So when you do that, if you plot the voltage and the current onto the graph, then you're going to see a linear plot in here. This slope will give you 1 over R. That R is, we call it as the resistance of the circuit. That may be your light bulb, whatever device that you use, right? So that means I and V are proportional to each other. That's why you will see this proportional graph, right? So now if I connect by using the your constant, then we will be able to write the voltage of any device with resistance R. We will be able to write that as I times R. That is what the Ohm's law is. Ohm's law is basically give you the relation between V and I. So V is proportional to I. The constant is the resistance of the circuit. Okay, so now as soon as you see that in here, you know that R will be, you can write if you want, it will be the ratio of V over I. Then this is you're going to measure it from volt. This is going to measure it from amperes. Then volt and amperes, volt divided by amperes, we call it as ohms. So that will be the units of the resistance. Okay. So now this resistance, actually we are not able to change. Again, similar to the capacitance, resistance also a manufactured value. So now how this value change? Usually most of the devices will follow the Ohm's law. There are some devices that does not follow the Ohm's law. That's why I have it in here. Material does not follow the Ohm's law. We call it as non-ohmic material. Non-ohmic. Material who follow the Ohm's law, we call it as ohmic material. Ohmic and non-ohmic. Okay, that's why I have that plot in there. Okay, so now when you go to the laboratory for your experiment, you're going to see the resistance. Then you will be thinking about why I have the colors on the resistance. Why do we have colors? Actually, those colors have the meaning. Those call it as color code, that by watching the colors, we can give you the value of the resistance. But since you are going to use multimeter during the experiment, you will be able to get the value from the multimeter. But if somebody thinking why colors are there, colors has meaning that will give you the value of the resistance. If I follow the rule of the color code, we can calculate it, but we are not going to do that. Okay. And as I mentioned, resistance is the manufactured value that will be calculated by using manufacturing informations. So now this resistance is proportional to the length of the conductor that you're going to use, and also it will proportional to the cross-sectional area of the conductor, 1/4 cross-sectional area, and it also give you the material informations, that is we call it as resistivity. So now finally, after this two follow-up formulas, I will be able to write the resistance, that is R, equal to some constant times length divided by the cross-sectional area. So usually we have cylindrical shape wires. Because of that cross-sectional area, you have it here, will be equal to pi and R squared. If you use the diameter, you know how to convert radius into diameter, then it will be this one. Okay. So now this resistance I will be able to, by changing the length, by changing the cross-sectional area, I will be able to change the resistance. That is manufactured way that you can change. And also by changing the material, you can change the resistance. So now this rho symbol, we used rho earlier for the density, but this is not density. This is the rho symbol that we use for the resistivity. In physics, we are using a lot of symbols, that Greek letters, to define different things. Here, it is a resistivity. It is a characteristic of the material. Okay, it has the units. If you need ohms, meters. That means the resistivity is different for conductor to insulator, because their conductivity is different, their resistance is different. Okay. Okay, so now electric power. Electric power, you remember that power we define in your lecture number 2 or 3 as energy per unit time. So, but here we can define the same way, but for the electricity part. The power in the electricity part, energy is Q times V divided by time. That will give me a power formulas, I times V, and also this, all the formulas is for the power. Because of the Ohm's law, I can replace the voltage by using I and R, and back and forth. Then I will be able to write the power, 3 equations together. One is IV, other one is I power 2 times R, and below the voltage power 2 divided by R. These are the 3 methods that you can calculate the power. But what is the units of the power? We know it is watts. We discussed that earlier too. Okay. Okay, so now you may think, especially when you pay the electric bill or the power bill, do you pay it for the power or do you pay it for the energy? So the units that you're going to pay in your energy bill is actually kilowatts hour. Okay, so by watching here, you see that this is power, watts is power, and this is time. Power times time is the one that you are paying. Power times time, if you go into here, you will see it is energy. You're just going to do cross multiplication. That means you are paying for energy, not power. Paying for the energy. We are paying for the kilowatts hour. That means you are paying for joules, basically. Okay. Okay, so I just include this slide to get an understanding that we have 2 different current and voltage. One is alternative current and voltage, and second one is DC current and voltage. So DC means direct current or direct voltage. That means you have it is constant without changing with the time. But AC means you have changing of the current and changing of the voltage. So we use the AC Sometimes you use the DC, sometimes you need the steady current, like your computer, laptop, you need the steady power. Because of that, we use the DC for that, or DC converters for that. Sometime in your electric heater at home, main electric heater or the air conditioner, you need the AC power, because we need to do the some rotational things that we need back and forth current, that will need the AC current. Okay. Okay, so now we are ready to go into the resistors in series and parallel. Now, resistor is a device that have resistance. It can be light bulb, it can be heater, it can be fan. Any device you have it in your home is a resistor, right? So we use the symbol R to measure the resistance, and it is a tooth kind of symbol is the one that we draw to represent the resistor, right? So now, similar to the capacitor, this is series connection of the resistors. Now you have the same current of the loop, but they have different voltage. If I want to calculate voltage, I will be able to calculate by using Ohm's law. V1 equal I times R1, V2 equal I times R2, V3 equal I times R3, right? But they have same current. That's the important thing. It is a single loop. Then it is a series connection. Now these three, I will be able to reduce into one resistor, that is called it as equivalent resistance, that will be able to calculate here by using R equivalent equal R1 plus R2 plus R3. Right, so don't confuse with the capacitor. Capacitor, when you have them series, you're going to add 1 over capacitance. Okay, that's different when you come to the resistance. Okay, so you have equivalent resistance, or if they are series. But sometimes you may see the parallel resistors, right? So when you have parallel resistors, you have here you have voltage equal I1 and R1. Here I have I2 and R2 according to Ohm's law, V. And here I have V, I3, R3. But important thing is this voltage of three resistors is exactly same voltage you supply to the circuit. Then we call them as parallel resistors. When they are parallel, can be a light bulb, as I mentioned, right? When they are parallel, you will be able to calculate the R equivalent. That will be 1 over R equivalent equal 1 over R1 plus 1 over R2 plus 1 over R3. You keep adding them until you finish whole circuit. That is if they are parallel, right? So now it is very important that when you have parallel connection, your net resistance is smaller than the original resistance. When they are series, net resistance is greater than any of these original resistors, right? So that means you have a lower current in here because larger resistance, and here you have greater current because you have small equivalent resistance. So now it's very important that when you think about your home circuit, some of the light bulb connect in parallel, some of them are connected in series, but connection of series light bulb give you some different things that we don't want to happen. Example, if I have 3 light bulbs, if one of them go on, we'll say this one is gone, burn, then the rest of the light bulb will not work because there is no connection between here to here. That means it is not a good way of setting up your light. But parallel connection, it is good because if although this one is burned out, still these two will work because it's still current pass through these two. Okay? There are a lot of things inside those circuits that we do not have time to discuss in your class. Okay, and so now circuits are not always series and parallel. Sometimes some circuits are, especially your home circuit, is combination of many devices. Some of them are parallel, some of them are series, some of them are not parallel or not series. So according to that, we need to break down the circuit into the parts and solve it as we understand. In your class, it is not we're going to do mostly because it is a little advanced. So Kirchhoff rule is the rules that we need to solve this kind of complex circuit. Kirchhoff rules, there are two Kirchhoff rules. We're going to learn this. First one is the junction rule. So junction rule is first Kirchhoff rule that says that if you take the junction of any circuit, then current into the junction, this arrow represent incoming current to junction, and that should be equal to all the outgoing current from the junction. That's why this 7 equal to plus 5, because 5 going out, 2 going out, 7 coming in, then that is the charge conservation. That is called it as the first Kirchhoff rule, that is the junction rule. Okay, so junction, everybody can understand, those all are junction. These are junction that you can have in circuit, right? That will follow for any junction in the circuit. And second Kirchhoff rule is, we call it as potential difference rule or the loop rule. So loop rule explaining that if you start from one point of the circuit, if you walk through the circuit and come back to the same place, potential will be 0. But you need to keep adding the sources and keep adding the resistance according to special sign convention. So I'm going to explain the sign convention in a minute. But before that, let's start with the point D. We'll say I'm going to start D. So when I travel from D to E, I pass through the 12 volt. This is my positive terminal. Then my voltage increase into 12. Right, you see here, 12. And then no change until I come to this point. This point I have still 12, but when I jump from this resistor, you will see this is 12A point, and then my voltage will be drop I times R amount in here. Because of that, my voltage is dropped into value in here, right? And then it's constant in here again, we go here, drop another amount. And then you're going to come back to D, then you still have the same voltage 0 that I start at the D. That's the potential difference rule or the loop rule or second Kirchhoff rule. Okay. So now what is the sign conventions we have? In your class, we are not going to solve advanced circuits, right? But a simple circuit that you need to think. So there are sign convention. When you use this formula, you need to think about some of the things. One thing you need to think, when you see the battery, you will need to think which side is positive, which side is negative. If your positive side is opposite direction to your loop direction, the blue arrow is the loop direction. That means the way that you're going to travel. Simple example, earlier you remember that I start from here, I am traveling in the loop in this direction. That is what direction? That is clockwise direction. So I travel in the clockwise direction. Now when I travel through the battery, I travel in right to left, right? And then my positive terminal is my left side, same direction as my loop direction. Then my epsilon will be positive. That will be in this case, that is positive. But if you have it is in opposite direction, your epsilon is negative. Epsilon is the voltage of the battery or power supply. Okay, that is one sign rule. And next sign rule is the resistance. So resistance, always you need to check the current direction. You need to check the current direction and the loop direction. So current direction in this circuit, you see that current is going this way, here also that way, right? And my loop direction is red one. Loop direction and current direction are the same. When they are same direction, you subtract the voltage I times R amount, because that you're going to drop the voltage when you pass from here to here, right? But if you have a case they are in opposite direction, you need to add it. Okay, that is the sign convention of the solving complex circuits. But in your class, we're going to think a very simple example. I have it in here, right? So now we're going to start with the battery, right? From here to here, first thing is you need to label your direction of the loop. This is loop direction. I choose it as clockwise. So now I'm going to start from somewhere. First, I'm going to start from the battery. So now when I go through the battery, this is my loop direction and my positive terminal, same direction as loop. Then I'm going to add it. That is epsilon 2L actually, right? And then I move into here. When I move into here, my current direction this way, it is same as my loop direction. They both are both are clockwise direction. Because of that, I need to subtract I amount your whatever that 400 resistance is, right? And then we go to the here, again your current direction and loop direction same. Because of that, you need to subtract I times 290. Then you will come back to end in the circuit, then it will be 0, right? Then epsilon equal to L, then you solve it for I on the circuit. So that is the Kirchhoff rule for the simple circuit. So we can advance the circuit and solve the problems when you come to the advanced level classes. But in your class, at least you should be able to solve this kind of questions by using the Kirchhoff rule. Okay, so only thing you can probably think, if I have example now, we'll say I have another battery somewhere here, but I have the direction positive terminal here and negative terminal here, 10 volt. So now your everything is the same, except that you have the another battery. That battery has the direction of loop and the positive terminal in other direction. Then you know that you need to do the another part in here, that will be negative epsilon 2 that you have as 10 volt, but 0, right? So according to that, you need to keep adding the things with the sign, then you're going to get the correct answer. Okay. Okay, so I think that's it for this section, and I will stop here. Did not stop the